All right. I feel like I hear someone's mic on. It's not a huge deal because it's quiet, but yeah, I do hear someone's mic. So please make sure you mute your mics, people. Okay. Um, okay. So we've been talking this chapter. Chapter 9 is all about the t statistic, and we've learned about two different ways of calculating the t statistic, two different forms of the t statistic. There's the one sample t statistic, which is shown right here. And then you also have the repeated measures t statistic, which is shown right here. The one sample t statistic is used when you're comparing a sample mean to a population mean, but the population standard deviation is not known. Oftentimes, the population mean will be chance performance, though the homework problem that we're going to do today is an example of an exception to this. Um, So one sample t comparing a sample mean to a population mean, usually this will be like hypothetical population mean or chance performance. But the really crucial thing is that you're comparing these two numbers, but you're using the sample standard deviation instead of the population standard deviation. For the within subjects t-test or the repeated measures t-test, also known as the paired samples t-test, three different names for this one test. These Ds are important. These Ds stand for different scores. And you use this t when you have a single factor with two levels, and it's a within subjects factor. Within subjects means that for each participant, they give you score for condition 1, and they also give you a score for condition 2. That's within subjects t-test, which involves different scores. And we did examples. I've done examples of both of these in previous lectures on chapter 9. And today I will be giving you another example of the one sample t-test for the homework. Let's see. Yeah. Okay. Um, so the first thing to start out, last time we were doing these problems right here. So we did this, this repeated measures t-test right here. We calculated t. I showed you all the work for this. So it was using these data right here. And we calculated all these Ds. These are the different scores. 5 minus 5 equals 0. 7 minus 3 equals 4. 6 minus 4 equals 2. 2, 2, 2. All those are 2s down there. And remember, for the repeated measures t-test, all of the information is based on those different scores. So we have m sub d, which is the mean of those different scores. And then here, these are the sum of squares of the d's. This is important because you use the sum of squares of the d's to calculate sample standard deviation, which I've shown you. I talked about that last time. Here's kind of the beginning of the work for how to calculate sample standard deviation, which I've shown you right here. The sum of the squares, 8 divided by 9. 9 we got from the n minus 1. 10 minus 1 equals 9. Take the square root of that. That gives us the sample standard deviation, which is used to calculate the estimated standard error, which you plug in right there. And this gives us this t value for the repeated measures t of 6.708. I also mentioned last time, though, let's move this. I also mentioned last time that you can if you have a repeated measures design like this, you can also do the one sample t-test. You can also calculate a one sample t given a very specific set of conditions. If when you add up condition 1 plus condition 2, it equals a constant number for all participants, which it does in this case, it always equals 10. 5 plus 5 is 10, 7 plus 3 is 10, 6 plus 4 always equals 10. Then you can also calculate one sample t, and it will give you the exact same number as you got when you calculated the repeated measures t, which is what I've shown right here. Here's the same data, but here's me calculating a one sample t, and I've shown you all the work. There's the sample standard deviation, estimated standard error. Here's the full t statistic right here. This is the exact same thing, the exact same data set. Once again, you can calculate one sample t because these numbers right here, all constant, it's the same number, 10. And we get the exact same t-value, 6.708. So one thing that we haven't talked about with respect to t too much, we have not talked about that much, is how to use the t-table to make a hypothesis test decision. So that's where we're going to really start out today. Using the same example, we're going to officially use that repeated measures t-test. So this is based, really could be used for either this one sample t right here, because it's 6.708, or the repeated measures t, because it's 6.708. But let's just pretend that we're doing it for one of those, the repeated measures t. So this t equals 6.708. Our degrees of freedom is 9, and we get that once again because there's 10 total difference scores, 10 participants, minus 1 is 9. We're going to assume 2 tails, which is kind of the standard in psychology, and it doesn't actually mention this, but we'll also assume alpha equals 0.05. In general, if the problem does not give you information regarding the number of tails in the alpha level, it's usually pretty safe to assume that it's 2 tails and alpha equals 0.05. Here it says that our critical t equals plus or minus 2.262. We need to determine why this is. So we need to go to our t-table and verify that this critical t is actually correct. So we need to look up degrees of freedom 9, 2 tails, alpha equals 0.05, and see what our critical t value is. So here's the t-table. You guys have t-tables to remind you. I believe it's on slide number 4 earlier on in chapter 9. You have this exact t-table. So for this example, our degrees of freedom are 9. Degrees of freedom on the left side right here. Degrees of freedom are 9. 2 tails is the bottom row here, looking at 0.05. So go to where 9 intersects with 2 tails, 0.05. You scroll down, you get 2.262 right there. 2.262 degrees of freedom 9. Alpha equals 0.05, 2 tails. You get 2.262, which is the exact number you see right here. Plus or minus 2.262 is our critical D. And I'll remind you that the null hypothesis is that the mu of D equals 0. That basically means if there's no difference between the attractive and unattractive faces in terms of the amount of time that the infant's been looking at the attractive and unattractive face, then on average, we should expect the difference scores to equal 0. Because if the infant is looking at the attractive face for 5 seconds and the unattractive face for 5 seconds, that is if there's no difference, 5 minus 5 equals 0. So if the infant spends the same amount of time looking at each type of face, that is if there's no difference, then when you subtract the amount of time looking at each condition, the attractive minus the unattractive condition, on average you should get mu sub D equals 0. The difference score should equal 0 if there's no difference in the amount of time the infants spend looking at attractive and unattractive faces. The research hypothesis does not equal 0. Mu sub D does not equal 0. So here I'm showing you a drawing of the distribution to help you kind of picture, should we accept or reject the null hypothesis. Here's the calculated t, 6.708 for our repeated measures t-test. Here are those critical t values right here, negative 2.262, positive 2.262. Not shown, but inferred, is that the center of this distribution is t equals 0, which should be in the middle of this distribution, t equals 0 right there. You shade in the critical regions. 6.708 is over here, way in the right tail, so you would reject the null hypothesis. The calculated t is in the critical region because it is bigger than this critical t right here, 2.262. Therefore, this t is in the critical region, and we reject the null hypothesis. Any questions about using the t-table to make a decision regarding whether to accept or reject the null hypothesis? All right, we'll have a little bit more practice with that in a second. First, though, we're going to talk a little bit about confidence intervals for the one sample t-test. We will not be dealing with confidence intervals for the repeated measures t-test. So confidence interval here, we've done confidence intervals before. Chapter 8, we did confidence intervals for the Z statistic. Now we are doing confidence intervals for the T statistic. It's not really that much different. There's a couple small minor changes, and that's it. So let's kind of investigate those differences. So just like the Z statistic, you have these two things you have to calculate, the lower bound and the upper bound. The lower bound, this basically tells you the critical region on the left side of the tail, the left side of the distribution. And this tells you, the upper bound tells you the critical region on the right side of the tail. I want to remind you that another thing, which is all confidence intervals have in common, is that for confidence intervals, the thing which is in the center of the distribution is the sample mean. When we do the traditional hypothesis test method, which is what I just showed you, for instance, on the previous slide right here. Let's see, I'll go to it. This right here, this is the traditional hypothesis test method, where the middle of this t equals 0 corresponds to the population mean. This is the traditional hypothesis test method. When you're doing the confidence interval method, which gives you the exact same decision whether to accept or reject the null hypothesis, instead of using the population mean in the center of the distribution, that is t equals 0, the population mean, we're going to be using the sample mean. That's how confidence intervals work. The sample mean is the center of a confidence interval, not the population mean. So the differences then between doing a confidence interval for t than for z is that we're going to have different critical values right here. Negative critical t and positive critical t. I feel like I should interject real quick or point out that in the textbook, they don't say critical t here. They just say t. And so I've added the word critical, but that's really important to know that these numbers right here, these critical t's, these aren't numbers that you are going to calculate. You always find these numbers. For the z, I just told you to memorize them. It was like z is 1.96 or z equals 1.65, depending on if it's 2 or 1 tails. When we're dealing with t, we don't have to we're not going to calculate these critical t's. We're going to look them up in the t table. So that we'll get practice doing that in just a second. So these critical t's you look up in the t table. So that's one minor difference, is that we're using critical t's instead of critical z's, and we have to use the t table to find these critical t's for a confidence interval. This right here is another minor difference. This S sub m is the estimated standard error. When we're doing the confidence interval for z, we use the population. We use like sigma sub m, which is the standard error. If you recall, the estimated standard error, the formula for that is S divided by the square root of n. That is the sample standard deviation divided by the square root of n. That is the estimated standard error because it uses the sample standard deviation. When we're doing z, this would be sigma sub m because we were using the population standard deviation. For z, it is sigma divided by the square root of n. So this is estimated standard error instead of standard error. That is S sub n m instead of sigma sub m. And then you add the sample mean. So structurally very similar to when we did this with z in chapter 8, except now we have a critical t here instead of critical z. And this is estimated standard error here instead of just regular standard error. Yeah. So now we'll go ahead and do a problem number 1 from homework. The reason I'm doing this is because it's a good example of a confidence interval. So I guess you can read along here, but I'll just read this to you and kind of explain things as we're going. We'll be making a confidence interval for one sample t-test problem like this. Okay, so an all-women's college is interested in knowing whether it places more or less females in male-dominated careers such as engineering, as compared to national data. According to the national data for the National Center for Educational Statistics, only around 22% of the people in engineering in 1990s were female. So this 22% right here, this is basically going to be our population mean. For this problem, assume that this population parameter has remained constant over time. So 22%, this is basically our mu. I will point out that in this problem, they're giving us basically what is our mu, our population parameter, or the mean, but they're not giving us a population standard deviation, which is the reason we have to do the t statistic. If we knew population standard deviation, we would do z, but we don't know the population standard deviation, so we're going to do the t statistic instead. The alumni data at this all-women's college remained the alumni data at this all women's college has observed the percent of graduates placed in male dominated occupations for 20 years. So this is kind of a interesting way of this is usually sample size would be like 20 different people. But in this particular study, they're considering the sample size 20 different years. So they collect data on females in male dominated careers over 20 years. Each year is considered like a participant. So our sample size is 20 because we have 20 years. The sample mean for those 20 years is 23.7% with a standard deviation of 6.1%. So the 6.1% right here, this is our sample mean. This is our sample standard deviation. 23.7% is our sample mean. The 6.1% is our sample standard deviation. We want to test the hypothesis that the amount of women in these male-dominated occupations has changed over the last 20 years as it was compared to the 1990s. I want to point out, it says test the hypothesis that the women's college average is different from the national average. The way this is worded implies a two-tailed test because it's not directional. It says test the hypothesis that the average in the last 20 years is different than it was in the 90s. Different can mean two things. It can mean either the amount of women in male-dominated careers has increased since the 1990s, or it's possible that the amount of women in male-dominated careers has decreased since the 90s. So that's a two-tailed test because it just says kind of vaguely different, which implies that it could be different on the upside, greater than, or it can be different on the other side, less than. So let's do the following three questions. What are the hypotheses in formal statistical notation? So that means null and research hypothesis. Then we are going to compute a 95% confidence interval. And then we will use that confidence interval to decide whether we should accept or reject the null hypothesis. We're doing this because I've mentioned before that you can use the traditional hypothesis test method, or you can use the confidence interval method, and they both give you the exact same decision as to whether accept or reject the null hypothesis. So for this homework problem, they'd ask you to do the confidence interval method, and so that's what we are going to do. So first, let's determine what the hypotheses are in formal statistical notation. Reminding you that it says here, the research hypothesis, that women's college average is different. That implies two tails. So let's go ahead. So here are our null and research hypothesis. The null right here, the mean percentage of women in male-dominated careers for that 20 years since the 1990s. So the mean over that 20-year sample is equal to the population mean, 22%. That's our null hypothesis. Basically, this is saying that in the last 20 years, the amount of women in male-dominated careers is the same and has not changed since that original population number that was taken in the 1990s, 22%. Null hypothesis. There's no difference. The research hypothesis is the amount of women in male-dominated careers for that 20-year sample is different than the population mean of 22%. I'll remind you once again, this is implying a two-tailed test because it says does not equal. And when something says does not equal, there are two things that are implied, or there are two possibilities. When it says does not equal, one possibility is that the mean is greater than 22%. That's one tail. The other is that the mean is less than 22%, which is on the less than side. Does not equal means that it's possible that the number is either greater than or less than. And so whenever you see this does not equal, that implies two tails. Any questions or comments about those null and research hypotheses? Those are the null and research hypotheses for this problem. So now, the fun part, computing the 95% confidence interval. So that's what's shown right here. So our degrees of freedom is 19. Can someone explain to me why the degrees of freedom is 19? How did we get that number 19?
It's n minus 1.
Yes, 20 minus 1. The amount of years 20 minus 1 gives us degrees of freedom equals 19. The size of our sample minus 1. And so we're going to assume a two-tailed test with alpha equals 0.05. That's pretty standard. But we have to look up the critical T to determine what the critical T is when you have degrees of freedom equals 19, two tails, alpha equals 0.05. So let's do that. Let's make sure. It says plus or minus 2.093, but let's just verify. Let's make sure that that's right. So degrees of freedom equals 19 is right there. We're doing two-tailed test. So we're going to use the bottom row with alpha equals 0.05. So go to where this intersects with degrees of freedom equals 19. And we got right here, 2.093, right there, 2.093. That is our critical T value that we will be using to plug in to our confidence interval equations, which are right here. So yes, we verified that the critical T is 2.093. And so we can go ahead and plug that in to our, we have, for the confidence interval, you're always going to have a lower bound, the left side of the distribution, an upper bound, which is the right side of the distribution. And you can see that we're plugging in the critical T. We have the negative critical T for the left side and the positive critical T for the right side of our confidence interval. We also have this thing right here. This is the estimated standard error, 1.364. And you multiply the estimated standard error times the critical T right here. I want to make sure that we understand how to calculate this estimated standard error. I've kind of plugged it in right here, 6.1 divided by the square root of 20. So let's go back to the problem real quick. That 6.1 comes from right here. The sample standard deviation is 6.1%. The sample size is 20. So the sample standard deviation divided by the square root of 20, that gives us the estimated standard error, which is 1.364. Plugging that in right there, plug that in right there. And then we just add 23.7. 23.7 is our sample mean. Once again, that comes from right here. The mean of those 20 years is 23.7. That is our sample mean. You plug that in right there. You just do the math. And then the lower bound is 20.85. The upper bound is 26.55. I will point out that the very center of this distribution, if you took what number, if I asked you the question, which is if I asked you the number, which is the very center of this confidence interval, the answer is 23.7. The number which is right in the center of this is 23.7. And then to use the confidence interval method, the thing that you do is you decide, okay, is the population mean, which in this study is 22%, 22, is it in the confidence interval? If the population mean is in the confidence interval, you accept the null hypothesis. If the population mean is outside of the confidence interval, then we reject the null hypothesis. Our population mean was 22. Once again, I'll show you from the problem. Right there, that's the 22. 22 falls within this confidence interval. 22 is within this confidence interval. Therefore, we accept the null hypothesis. We are not willing to conclude that 22 is significantly different than 23.7% because 22 falls within the confidence interval right here. So we accept the null hypothesis. So that's the whole darn problem, basically. So yeah, that's it. Any questions or comments about this homework problem? All right, we got one more homework problem. Here's another one. I believe this is homework number 2, homework problem number 2 from homework 5 written. Okay, so this is an example of a one sample t-test. So yeah, I'll read it to you here. A researcher is interested in whether infants' attention to their mother's voices increases in the first week of life. Let's assume that an established baseline exists, that is a population mean, showing that infants attend to their mother's voice on average for 5.867 seconds on their first day. So this number, 5.867, we're going to assume that this is the population mean. You got to, we assume that we've collected data from the entire population of infants on day one, showing that on average, the population of infants spends that amount of time, 5.8667 seconds, paying attention to their mother's voice on day one. One thing that I feel I should point out is that this is kind of a weird example, because in real life, it is very rare that you would have the population mean, but you would not have the population standard deviation. There's really no reason you would ever know the population mean, but not know the population standard deviation. Nevertheless, in this problem, they do not give you the population standard deviation. So we have to use the t statistic instead of the z statistic. Once again, if you know the z statistic, or sorry, if you know the population standard deviation, then you use the z statistic. In this problem, they don't give us the population standard deviation, so we have to use the t statistic. So they give you the population mean, though they don't give you the population standard deviation. A little weird, but we'll roll with it. We'll do the t statistic for this problem. So there's 15 infants, that's our sample size. And the researcher tests the number of seconds that the infants pay attention to, oriented to the direction of, the mother's voice on day 7. So the population data are on the very first day, day 1. You have infant from all babies in the population on day 1, but we have only a sample size of 15 infants on day 7. And what we want to know, we're going to use the one sample t-test, is the sample mean based on 15 infants, is that sample mean significantly different than the population mean from day 1? So here are the data, the amount of seconds each infant spend paying attention to the mother's voice. There are 15 numbers here. Those are our 15, these are the scores for our sample size of 15. Each one is a amount of time in seconds. We want to test a hypothesis that the attention to the mother's voice increases over the first 7 days of life. That is, on day 7, our hypothesis is that the amount of time that the infants spend attending to the mother's voice will be greater on day 7 than it was on day 1. So I want to point out that this hypothesis is directional, because it is a one-tailed test, in other words, because we're hypothesizing that the mother's voice increases on day 7 relative to day 1. So it's making a specific prediction. It's increasing, the amount of time increases. That suggests a one-tailed test because we have a directional hypothesis. The only thing that we're contemplating, the only thing that we're considering is the possibility that the amount of time increases. If we had said it more vaguely, more generally, like we are testing the hypothesis that the amount of time the infants spend paying attention to their mother's voice on day 7 is different than the amount of time they spend paying attention to the mother's voice on day 1, that would be two-tailed. But we have a directional hypothesis here. We're specifically saying it increases on day 7 relative to day 1. Therefore, this is a one-tailed test. So what are the hypotheses in formal statistical notation? I have those right here. Our null hypothesis basically says that the amount of time that the infants on day 7, those 15 infants, the null hypothesis predicts there's no effect. So the amount of time that they spend looking or paying attention to the mom's voice should be equal to the population mean. Because it's a one-tailed test, though, we'd also say it's equal to or less than the amount of time that the infants spend relative to the population mean. So the amount of time the infants, those 15 infants on day 7 spend looking, paying attention to the mom's voice should be equal to or less than the population mean. The research hypothesis, H1, was directional. Once again, you can see that this is a one-tailed hypothesis because we just have the inequality here. If this was a two-tailed test, you would have the equal sign with the line through it, which means greater than or less than. This is a one-tailed test, so we just have the one inequality. Our prediction is that the infants, the amount of time they spend paying attention to the mother's voice on day 7 will be greater than the population mean. It'll be greater than the amount of time the infants spend looking at paying attention to the mom's voice on day 1. So these are the hypotheses. Any questions or comments about our research and null hypotheses? All right. So now we draw the distribution with our uh, critical values and critical regions, which is shown right here. So our degrees of freedom is 14 because we have 15 babies, 15 infants. 15 minus 1 is 14. We are going to assume one tail with alpha equals 0.05. And our critical T is 1.761. So let's verify that that critical T is correct. All right, so we're going to degrees of freedom equals 14 right there. One tail test, so we're using the top row here, but we're still using 0.05, alpha equals 0.05. So we're up here and we're going down to degrees of freedom equals 14 and we get 1.761 right there. 1.761 right there. That is our critical T. And you can see it right there. So I have a question. In this distribution, I only have one critical region. Why is that? Why do I only have one shaded area on this distribution?
Because it's one-tailed.
Good, thank you. Yes, this is a one-tailed test, and this one critical region is our one tail. So we have 5% of the distribution falls to the right of this critical value right here, this critical T value, 1.761 right there. Okay, so we've drawn the distribution with our rejection region, our critical region right there. Now we need to compute the test statistic and show where it falls relative to our distribution. So here is where I've calculated part of, actually, okay, so here is, yeah, we've got to do this backwards. So here is where I calculated T right here. So this 7.2 is a sample mean. It was calculated by taking the 15 scores. Each of these is the amount of time that the baby spent looking at or paying attention to the mom's voice on day 7. These 15 scores. Add up those 15 scores, divide by 15. That gives us the sample mean of 7.2. 5.867 is our mu. It is our population mean. This 0.2 right here, this is our estimated standard error. You can see I calculated that right here. I want to remind you, though, that the way you calculate estimated standard error is you take the sample standard deviation and you divide by the square root of n. You take s divided by the square root of n. So I want to show you that. I've calculated that for us, I think. Yeah, well, I've showed you how to calculate sample standard deviation right here. And so S equals 7 minus 7.2 squared. The way I got that is you take this first score right here, 7, minus the sample mean, 7.2, and then you square that, and then you write that number down. You go to the next one, 7, you see the 7 again, minus the sample mean again, 7.2, square that difference, write that number down. Then you go to the next number, 6, because we got a 6 right there. 6 minus 7.2 squared. You write that number down. And then you would do this 15 total times just to make sure that you're able to kind of extrapolate the pattern. I haven't written it down, but what would the next one be? Can someone tell me what would the next one be right here?
8.
Yeah, finish, do the whole thing though.
Sure.
Yeah.
8 minus 7.2 squared.
Yes, thank you. 8, which is this number right here, minus the sample mean, 7.2, in parentheses, and you square it, write that number down. You have to do that for all 15 of the scores. Then all 15 of the scores will be up here on the numerator. You add them all together, and then you divide by 14. This 14 is n minus 1, the amount of scores minus 1. You take the numerator divided by 14, and then you take the square root of it. That gives you S. So if you were doing this problem, you would have to calculate the sample standard deviation by yourself because it's not given in the problem. It's right there for you. Then to calculate estimated standard error, you take this number, 0.775 approximately, and then you divide it by the square root of, tell me, you divide it by the square root of what?
N.
It is N, which is 15. And so that was good. I want to remind you that when you're calculating sample standard deviation, you're dividing things by N minus 1. But when you're calculating estimated standard error, you're just dividing it by square root of N. You don't subtract N minus 1 when you're doing estimated standard error. It's just this square root of N, this good old-fashioned N in the denominator for the estimated standard error. Okay, so once again, here's how we calculated our T. This is the sample mean, which you got by taking the mean of these 50 numbers. This is our population mean. This is basically the mean amount of attention on day 1. This is like the population number. And then estimated standard error is 0.2. You work out the math here. You get our T value is 6.67. I want to remind you that our critical T value was 1.761. And so then looking at our problem here, the next thing we're supposed to do is make a decision and communicate the results. Make a decision whether to accept or reject the null hypothesis. And so this is copied and pasted directly from the answer sheet. I want to point out that Susan Marshall, when she made this picture right here, she must have been using a different T table with slightly different numbers. She had the critical T value being 1.762. Our T table said it was 1.761. Those are close enough critical T's that I would definitely, either one would be considered right. They're very, very close to each other. I just want to point out in case you're confused, she must have just been using a different T table, which had a slightly different number in the thousandths place, that 2 there. But you can see that our calculated T of 6.67, we just calculated that using our T formula, is way out here in the tail. It's way out here in the tail. And so we would reject the null hypothesis. That is, we would conclude that the amount of time that the infants spent paying attention to their mom's voice on day 7 was significantly more time than the amount of time they spent paying attention to their mom's voice on day 1. That is, the sample mean of 7.2 is significantly greater than the population mean of 5.867. This is an example of a one sample t-test. I think that's all for that. Any questions or comments about this? This is problem number 2 from homework. Any questions about this one? All right, there's only one more thing to talk about today, and that is this right here, Cohen's d. I don't remember off the top of my head if there's a Cohen's d problem on the homework, though this type of thing could show up on the test. At this point, I don't think calculating Cohen's d would be considered that difficult for people, so I'm not going to spend time doing a problem in class. We have done Cohen's d, and you did do some of those in the most recent test. You have done Cohen's d problems before. You did it with the z statistic back in, I believe it was chapter 8. I want to remind you that when we're doing the z statistic, the thing that we know that we don't know for the t statistic is in the z statistic, you know the population standard deviation. For the t statistic, we do not know the population standard deviation. Instead, we will use the sample standard deviation for the t statistic. And this basic difference between z and t is you can see when you're looking at the equation for Cohen's d right here. Here is the equation for Cohen's d when you're dealing with the t statistic. The numerator is the exact same as the numerator for Cohen's d when you're dealing with the z statistic. That is, the sample mean minus the population mean. So the numerator for d hasn't changed. And we've seen it in chapter 8. We're seeing it again in chapter 9. In both situations, the numerator was m minus mu. However, the denominator has changed. This is S. This is the sample standard deviation. When we're calculating Cohen's d for the t statistic, we don't know the population standard deviation. That is, we don't know sigma. So we divide by S instead. That's the best we have. So that's the only difference compared to Cohen's d in chapter 8. In Cohen's d in chapter 8, it was m minus mu divided by sigma. That was for z. In chapter 9, when we're calculating Cohen's d for the t statistic, it's m minus mu divided by the estimated standard, the sample standard deviation, S. And I'll remind you that in general, Cohen's d is a measure of effect size, and measures of effect size, like Cohen's d, they tell you how far apart the two means are, the sample mean and the population mean, in terms of standard deviation units. How many standard deviations apart are the sample mean and the population mean from each other? That's what Cohen's d tell you. When you're doing the z statistic, it's sigma in the bottom. When you have the t statistic, it is s in the bottom. So that's all I have. If people want to stick around and ask some questions about whatever, that's fine. I'll be here. That's all I have planned for lecture for today.